All right, this is a video on inverse variation, and we'll start with an introduction and then do a few solved examples. As a reminder, before we get into inverse variation, I want to remind you about direct variation, something you have actually been working with for quite a while. We can say that y varies directly with x if y is equal to k times x. You've actually probably not used the letter k, you've probably used the letter m. M would be the slope in this case. So if we have a line with an y-intercept of 0 and a slope of k, we can say that y varies directly with x. What that really means is that x goes up, y goes up as well. As x goes down, y goes down as well. And they're related to each other by that slope of k, by that proportion k. Inverse variation, in contrast, we can say that y varies inversely with x. We can say something like this: y is equal to k over x. We could also say that x times y is equal to k if we were to solve for k. What that really means, when we have things that are inversely linked, if one variable increases, the other variable will decrease. So as x goes up, y would go down, and vice versa. I think of these as sort of like a seesaw. As one goes up, the other goes down. Okay? So if x and y, if the product of x and y is equal to a constant k, as I'm showing right here, then we would know that they are inversely related. So we can answer this question, is it inverse variation, by simply looking at the product of x and y. If x and y have a consistent product, then they are linked by an inverse variation rule. So looking at this first example, 2 times 15 is 30, 4 times 7.5 is also 30, 10 times 3 and 15 times 2 is also 30. So what we can determine is that k equals 30. And we can say that, yes, there is inverse variation happening here. Y is inversely linked to x, inversely related to x, and we can even come up with an equation, y equals 30 divided by x. Okay. In contrast, this second example, 2 times 10 is 20, 4 times 8 is 32, 10 times 3 is 30, 15 times 1.5 is 22.5. So we are not getting a constant product, so this is not inverse variation. Okay. Second example, we can look at this example where we're trying to determine the relationship between x and y, and then use that relationship to predict a future value of y. So for this example, suppose x and y do vary inversely. We need to know that in this case. So that's important to know, that x and y vary inversely. Determine a function that models the inverse variation if x equals 4 when y equals 12. And then determine the y value corresponding to x equals 10. So we need to find k. We know that y equals k over x, or x times y equal k. So if we are given this one particular set of x and y values that are part of this function, we can determine that 4 times 12 is 48. So k is equal to 48. All right? And then we can write our equation. Y equals 48 divided by x. Okay, so this equation would represent the inverse variation in this case. And now we can find y if x were to be 10. So y equals 48 over 10. So y equals 4.8. All right, x and y vary inversely in that situation with a constant product of 48. There are some combined variations that things get a little bit more complex. We won't do many examples with this, but we can say that if z varies jointly with x and y, we're introducing a third variable. So in this case, x and y might be our two independent variables that determine what z is equal to. So if z varies jointly with x and y, we can say that z is equal to some constant k times x times y. So if x gets larger, z gets larger. Also, if y gets larger, z would get larger. We don't necessarily know how x and y themselves are related, if they are, but we do know that x and y both contribute to z. Separately, we could say, we could consider, what if z varies jointly with x and y, but inversely with w? So we could say that z varies jointly with x and y, and there's that constant k that we're including in here, but it varies inversely with w. So w would be in the denominator. So again, in this case, if x and y were to increase, z would also increase. However, if w were to increase, z would decrease, okay? So z and w are inversely related. And as a third particular example, if z varies directly with x and inversely with the product of x and y, that's a mistake. Let me change that. That should be the product of w and y. Okay. So again, z varies directly with x and inversely with the product of w and y. So we have a constant of variation k being multiplied by x up top, and then the product of w and y down below. So again, in this case, if x were to increase, z would increase, and if either w or y were to increase, z would decrease because they're on opposite sides of a fraction. Let's do one example related to that. The number of bags of grass seed needed to reseed a yard varies directly with the area to be seeded. Think about if that makes sense. The larger the area to be seeded, the larger number of bags you need. That makes sense, right? And inversely with the weight of a bag of seed. So as the weight of a single bag of seed goes up, the number of bags you need goes down. So that makes sense as well, that those would be inversely related. If it takes 2 3-pound bags to seed an area of 3,600 square feet, how many 3-pound bags will seed 9,000 square feet? So let's write out a general form here, analogous to what we were just doing up here with the combined variations. And then we'll plug in some numbers and find our constant of variation here. So the number of bags of grass seeds, I'll do n for number of bags. It varies directly with the area, so we have a constant of variation here being multiplied by the area that we're working with, and it varies inversely with the weight. So weight will be on the bottom in this case, in the denominator. All right, and now we can throw in some numbers. So if it takes 2 3-pound bags, so we have two bags. We don't know what k is. We're going to try to figure out what k is, and the bags are 3 pounds each, to seed an area of 3,600 square feet. How many 3-pound bags will seed 9,000 square feet? So we're going to, before we address the 9,000 square feet problem, we're going to determine our constant of coefficient, or our constant of variation k. So we're going to multiply both sides by 3. And these 3's will cancel, and we can get 6 is equal to 3,600 times k. Divide both sides by 3,600. And I think we could determine that k is a tiny decimal, but probably easier to express as 1 over 600 once we simplify that fraction on the left. So now we can write out our specific equation for this particular scenario. We have our number of bags is 1 over 600 times the area in which we have to seed divided by the weight of a single bag. And now we can plug in the particularities for this 9,000 square feet situation. So the number of bags will be 1 over 600 times 9,000 square feet divided by the weight of a single bag, which is 3 bags. I'm going to try to run through this in my head. I'm going to work with 9,000 over 3 first. That seems to be pretty friendly. So I'm going to get n is equal to 1 over 600 times 3,000. And 3,000 divided by 600 would be 5. So that would be our solution there. We would need 5 bags in that particular scenario of a 9,000 square foot area needing to be seeded. The important thing to keep in mind, though, is that we have something that varies directly and something that varies inversely. So direct variation is going to be in the numerator of our fraction. Inverse variation is going to be in the denominator of our fraction. And that's a good place to stop right there.